Hi everybody, welcome to this last part of the Fisher 800B restoration series. This is going to probably be a pretty long video because of how much I got involved in when we got to the multiplex section of this tuner. And I also got into a little detail of how to kind of go through and analyze a tuner, both the AM section and the FM section, a few tricks that I use that may not be in the book anywhere. And then we go through the complete restoration and troubleshooting of the multiplex, which is very old. Here's another one. This is a little bit newer version of the same thing that we worked on. And this is actually a module that can be plugged into these and into a lot of the Fisher receivers of the time to convert it from a mono FM to a stereo FM. It's very different the way that it works compared to a modern, well, even an old modern 1970s vintage stereo multiplex tuner. So we'll get into that. We'll see just how archaic this design is and some of the inherent quirks that you have to deal with if you're going to use these. So I hope you enjoy this video, and I'm not going to edit a whole lot out of it. I'm going to leave a lot in, and it will be a long video. I don't care. You can all skip through the parts you don't like. I'll try to index it so you can kind of jump around. I know people will repeat watch some of my videos. I've gotten some comments, and you kind of use them as a reference when you're working on some of your own gear. So I'll try to do that for you to make it a little easier. But really there was a lot of interesting things that I ran into, so I thought I would like to share them with you. And so that's why I thought I'd put this little introduction in the beginning of this video. Afterwards, I'm going to kind of lay off the restorations for one project here because I actually want to make another update to the bench. And what I'm going to do is I'm going to make a much nicer version of my electronic circuit breaker. To add some features in it that I'd like to have. I may or may not do a video on it. Not sure. I'm going to share some of the instructions and things on Patreon for some of the patrons to look at. But if I do decide to shoot a video of it, I'll post it, and we'll see. We'll see what kind of time I have. It's been very busy at work. This video has gone over the span of several weeks, and I forgot where I left off and so forth, so it jumps all over the place. So it'll be interesting. Enjoy, and we'll see you soon. Hi everybody, welcome back. Well, I can tell you right now, if I wanted, I could make this a very short video because this is the section where we're going to do the tuner alignment and so forth. But I can tell you after just kind of a quick little checkup, this thing probably will not need any alignment. And if it does, it's just going to be a tiny little bit. I don't think we're going to make much improvement. That said, I mean, there could be some things that need done. I don't know. But just preliminary testing, I would say that very little is going to need done with the alignment on this. Famous last words though, huh? But what I will do is we will at least go through the process and set up the test equipment and at least look at it. Now I did a pretty extensive, I've done quite a few extensive alignment videos over the years, and some of them were conventional, some of them were unconventional. We'll try to follow the instructions on this one just so you can see it, but again, this thing's in pretty good condition considering, and it's loaded with these IF cans that you see here, and these are the ones that are notorious for getting the silver mica disease. But as I said, I believe this was stored in a nice dry environment, because so far none of the, other than this one electrolytic that was really bad, and you can see it kind of leaked and popped apart, and those two can capacitors that were bad, The rest of this thing is was in surprisingly good condition. So if you're interested in seeing that, that's what we're going to do in this video, and stay tuned. Now, the first thing that I've done, just to do a quick evaluation, this is before I even opened the manual or any kind of thing like that, is I just set up a basic, I'm at 1100 kilohertz or 1.1 megahertz. I have 33% modulation, and I'm using my little radiating jig that I have here, which is nothing but a loop of wire, and it's connected to a little short piece of coax going into a little BNC connector. There is all this is. And really, by using this method, you can't really go by the drive signal, because of course the coupling between that coil and your antenna and all that, you're not going to get any any accurate readings. But driving a 1 millivolt, because this is times 1000, so you have 1 microvolt times 1000, so you have 1000 microvolts, which is 1 millivolt. That would be into a 75 ohm load, which of course this is not what we have. So take it for what it's worth. That being said, it's a pretty weak signal. I know that from experience because of this coil. And if you can receive a station at that, you're not doing too bad. And again, the distance from the coil to the antenna and so forth is going to affect all that. But anyway, let me give you a bird's eye view here of what we're doing. So I need to turn off some lights here to begin with so that you can see a little more clearly what's going on. But down here is the antenna. It's a bar antenna. And you can see as I move the coil near it and away from it, and you can hear, I have it, there's your speakers. See there? And if I just take it and kind of put it over top of the coil or of the antenna, there's what you have. Okay, and then see if we have to turn some lights out. No, I think we can see. So you can see how clear that signal is. And I'm looking at the record output jacks. So this is the demodulated audio. It's a 400 hertz tone. And this is after it's gone all the way through the tuner, through the IF stage, through the AF stage, into the amplifier. And it's coming out of the record output jacks. So of course it doesn't go through the power amplifier, but through the preamp section anyway. And there you go. And you can see how clear that is. It's not moving around. There's no static. If we turn down the signal strength, you see how it starts getting a little bit wavy. The amplitude drops. You start seeing that kind of noise on there. That tells me that, that's where the signal's starting to break up. And if you listen, you'll hear static now. A little bit. Still not too bad though, right? And if I go even more, you'll hear more static. Okay. So, and you're hearing that little chirping. Hear that little chirp, chirp, chirp. Chirp, chirp, chirp. That's a power supply on my bench that it's picking up. So anything with switch mode power supplies or anything like that, it can affect that. Know your bench, know your environment, and know your test equipment. That's the biggest thing. And what I'm doing doesn't need a Sencor SG80. You can use any AM signal generator with modulation. Even like an old ICO 324 or something, anything would work to do this basic test. You just have to kind of get used to doing things like that. So what can we tell by looking at this? Okay. Well, we can tell that, first of all, the static is very symmetrical throughout the waveform. So it tells me that the detector is working pretty well. And again, because I know this coil that I use, I know that if I put a 1 millivolt signal into that, or at least what it thinks is 1 millivolt, which is not actually, because I'm not properly coupled to this coil, I know that I should get a solid signal. on a tuner that's set up properly. Again, not super accurate test. This is quick and dirty. Yep, it's working. That's all we care about right now. If we want to take more accurate measurements, we would have to actually feed the signal into a section of the tuner and trace it through, and we could actually make quantitative measurements, but we'll do that later when we use the instructions in here. Anyway, AM tuning is working well. Again, we were looking at 1100 kilohertz or 1.1 megahertz, and if you look at the dial accuracy on this, if it'll focus. All right. I got to back it up. There we go. Look where I am. It is absolutely spot on 1100. So, and I can go through the different frequencies and it tracks. So this thing's set up nice. And you can see I have a pretty nice signal, and it's the magic eye is showing properly. So this thing isn't going to need adjusted. And I can tell you when we get on to the FM section, it's probably going to be something pretty similar. And we'll take a look at that next. Right, we're now switched over to FM. And I'm just doing a mono FM modulation. Now this type of test, you have to have a signal generator that is capable of FM modulation. So my 8657 HP can do that. This can obviously do that. The Rigel DG 4162 can do that, but you're going to have to put attenuators on it to get the signal level low enough. Because it's not really a true RF signal generator, but it can do it. Anyway, this is going to take you a step up in test equipment to have that. That's what I'm saying. The low end, RF signal generators will only do AM modulation. So anyway, now I have it set to FM, and we're at 98 megahertz, and I'm modulating it at 90%, and that's kind of important. I'll show you why in a little bit here. And I have a 100 microvolt signal going into the tuner, because right now I'm more concerned about checking the IF and the discriminator and the dial accuracy. We'll get a little more into that in a little bit, but I'm just showing you some basic tests that you can do on any tuner. This works with transistor, tube, whatever, it doesn't matter. Anything that is an analog tuner, this is a good test to do. So anyway, we have our 98 megahertz, 90% FM modulation. I have a 400 hertz tone. You can hear it if I turn it up. All right, and you hear there's a little bit of static. That is by design. I did that on purpose. I'll show you why in a minute. And like I said, 100 microvolts. Looking at the output at the record out jacks for your tape deck, that's where we always monitor this with our scope. And I'm using an old analog scope. You can also use your digital scope. Doesn't matter. You're just looking at a basic sine wave, aren't you? And you see that signal, how it's jumping around? I did that on purpose, once again. What I did was I set the dials the way you see them, and then I reduced the signal level until I was just starting to get some static. And the reason we want that static, this is going to help us to determine, number one, it's going to determine when we're on center frequency on the tuner. It's also going to help us with kind of evaluating what the ratio detector, how the ratio detector or the discriminator is working in this thing. So notice the static is symmetrical on the top and the bottom. If I go off frequency, now I went above frequency there, and see what's happening? All of our static went to one end, okay? If I go to the other end, this side cleans up, and this side has the static on it. If I go and make equal static on both sides. I get it right to that point where I'm getting static on both sides. It kind of tells me that my discriminator circuit is working, or ratio detector, whatever circuit they're using. They all kind of are based on the same principles for the most part. So now I know I'm right on frequency, and if all's going well, our dial should say 98 megahertz, right? So let's go down and see. And look, pretty close, isn't it? Almost right on. A little bit high, but that's really good for an analog tuner. And we could probably adjust that and make it perfect, but it might throw some other things off. I'm not really going to worry about it. If it's that close and it works across the dial like that, I'm probably not going to mess around with it a whole lot. So you see how to get it set to center frequency just by using your scope and the record out jacks and your signal generator. Really simple, right? So we're now on center frequency, and we know the dial accuracy is good. We know the discriminator circuit's working okay, so obviously the IF must be working okay. I'm driving a 100 microvolt signal, which is not too bad, and with getting just minimal static. So now what we're going to do is we're going to drive the signal level down until we can still hear the tone in all of the noise floor and everything. And this is going to give us like our minimum signal sensitivity. So I'm going to stay on here for right now. I'm going to turn the volume up and listen to what that sounds like. Now let me take you up to the signal generator, and I'm going to back this out a little bit so you can see everything at once. And watch what happens to our signal, but more importantly, we're going to listen with our ears. And I'm going to turn this way down and see how far we can get and still hear the signal. And by the way, I'm feeding this directly into the input jack of the antenna jack of the tuner. Okay, here we go. Loud noises, but that's the only way we can do this. So right there is 10 microvolts. That's a pretty small signal already. And there is 1 microvolt. That's a 1 microvolt signal. And listen. You can hear a lot of static, right? But looking on the oscilloscope, it's turned into too much noise, but you can just barely follow that pattern of that 400 hertz. It's still in there. And if I go up to about 2.5 microvolts, I can see a very clear sine wave with all the static, and you can hear it. So what that tells me is at 2.5 microvolts, and again, the termination isn't perfect. I do have a 75 ohm cable. This is for 75 ohm termination, and that is a 75 ohm terminal on the back of the tuner, so it's pretty closely coupled. And you can see with 2.5 microvolts at the antenna jack, I'm getting an audible sound. And I can tell you that most tuners, when they're set up properly from this generation, that's how they're going to perform. This is why I told you up front that I don't think this needs aligned, and I would not do an alignment on this in most circumstances because of this. Now I can go through and we can do some other tests with frequency and so forth, but as it stands, that part is working. The only thing we need to check now is the stereo or the multiplex. Okay, so I'm now at 150 microvolts because multiplex signals have to be a lot stronger than a mono signal. So 150 microvolts is usually pretty good at the antenna terminals. I'm still on RF, and I'm now modulating it in stereo. So we have a 400 hertz stereo signal with pilot going into the tuner. And I have the tuner now set to multiplex stereo. I don't know if you could see that there, but it's multiplex stereo. And we are now using this add-on module. See it? And if we look at the scope, I already see a problem, but we'll talk about the problem later. But in general, we are getting a 400 hertz tone on each channel. You can see. And if you listen to it, it sounds pretty good. Of course, 400 hertz, how good can it sound? It's annoying to your ears, but to me, it's music to my ears. So even the multiplex circuit is at least receiving a signal. We don't know how it's doing stereo separation yet. We have to test that next. So what we're going to do is I'm going to go over to my multiplex generator, and this is where you need a higher end signal generator. You can't do this without a multiplex signal generator. Now you can get a separate multiplex unit and you can modulate it into like something like this 8657 right there where it says modulation input. You can actually put a multiplex signal in there and set it to FM modulation and set your frequency, and at the output there you will have a stereo FM signal coming out. But if you get one of these, and this isn't the only one, there's a whole bunch of different versions out there that will do it, but this Sencore is one of them that can do everything. It can do the modulation, the multiplex, it can do the RF carrier, everything all in one unit. So anyway, we're listening to stereo and you can see both channels. We're now going to go to right channel only and left channel only. And when we do that, we should see one channel go away and we should see the other one stay there. And then we go to the opposite channel, the channels should swap around. So here we go. We're going over to right. And you can see it kind of suppresses this. And if I go to left, it kind of suppresses that one. So you're getting a very weak stereo separation. All right. So that tells me one of two things. Either the multiplex module is not working or it's just out of alignment. Okay, so it either has a problem or it just needs an alignment. Looking at this, it needs an alignment and it needs a couple things. Number one, because we're not getting a flat line on this side when you select left channel or a flat line on this side when you're selecting the right channel, the separation is not adjusted properly. In addition, if I kind of open this up a little bit and I look at this little signal, you see how that is? See how zigzaggy that is? That should be a clean looking signal. And what you're seeing on there is you're seeing your pilot circuit. The pilot trap is not there. Okay? So there's an adjustment for that as well. And we need to fix that also. So everything in here looks like alignment. Again, I don't think there's anything broken. It just needs aligned. So why did I bother going through all this with you? Well, I wanted to show you how quickly and easily, if you have the right test equipment, that you can evaluate a tuner without really trying to go through all of the alignments and everything. And this is something that I'm big on this. I don't like to just blindly start jumping in and doing an alignment. I would much prefer to do an assessment first and then try to get an idea of what I might need to do so I can do as little as possible so I don't have to disrupt the factory alignment that's probably already in there. Now, of course, if the golden tweaker has been in there, all of these things will be a mess and it would show up very quickly. And you can tell by going to different frequencies and doing the different tests I just showed you, you can very quickly find out what parts of that tuner are not going to work properly. Does that make sense? And what parts need attention. This one, fortunately, needs almost no attention except for the multiplex circuit, which we can align very simply because this is a very simple multiplex circuit. And you're going to see it doesn't perform as well as, for instance, a modern digital circuit, or even a modern solid state tuner that may have PL, phase lock loop and different things, modern things, or synthesized tuners. There's all kinds of differences, but you'll be surprised how nice this thing can sound and how well it can perform for early 1960s technology if it is properly aligned. Okay, well, we did our evaluation. Let's go through, and now again, I'm going to look at some of the things in here, but we're not really going to touch the alignments. We're just going to look at them. Okay, for the AM alignment, we're going to just keep things old school. We're going to use a vacuum tube signal generator. This is just a RCA WR50B. It can do a couple things that a normal standard RF signal generator of this generation can't do, because it actually has a little sweep oscillator built in. So what we need is basically just an RF generator that can generate signals within the AM frequency band and the AMIF frequency band. You need some sort of a high impedance meter like this VTVM here. Any VTVM will work, or you could use your fluke meter or your digital multimeter with a high impedance input. The only difference is when you're looking at a digital meter, you're just kind of watching the numbers bounce around. I kind of like the needle, watching a needle on an analog meter. It is damped a little bit so that it doesn't flutter around so much. It's just a little easier to read. But whatever you have, use. It'll work. You also will need a capacitor. This is a 0.01 microfarad or a 10 nanofarad, however you want to call it. And I just attach a little alligator clip or crocodile clip to the end, but you don't need to do that. You can just use clip leads if you want. You'll need a jumper, and I'll show you what this is for later. And it doesn't have to be hooks. It can be the crocodile type. And you'll need a 220 picofarad capacitor, which I just grabbed one of these out of the bin. You can use a ceramic one. You can use a film one like this. It really doesn't matter. I don't even know if this is a film. This might be a stacked ceramic. But anyhow, it's a 220 picofarad cap. It's not real critical. So that's what we need. That's the setup. And if you want to use your scope, you have a scope, you can use it to monitor the signal. And I have my scope attached because I want to show you something. So the first thing we want to do here is always read the instructions all the way through before you start. The tendency with sometimes is to look at step one, read it, do it, and then go to step two, read it, and do it. What you're going to find out is when you try to do things like that, you'll get all the way down here and you'll realize that there was something you probably should have done ahead of time that you didn't do. So reading all the notes, reading everything through thoroughly, and understanding what it's telling you to do is key to doing any type of alignment properly. So you can see things like they want you to set the logging scale on the meter, or on the front dial. So the pointer has to be at the beginning of the dial, for instance. And it talks about all that. Signal generators, it tells you what kind of generator to use, they recommend. And you're going to see things like 30% modulation. Now, these old analog vacuum tube signal generators, they don't actually have these things. And you'll notice nowhere in here does it tell you how much output, like how many microvolts or millivolts of output. You don't do that in this old school stuff, okay? So we're going to do it the way they would have done it with what you would have had on your bench, for an average technician at the time. And they're saying you need a vacuum tube voltmeter. So you need a meter that's high impedance input. You don't really want to use something like a volt ohm meter like this, because a lot of times these will have too high or too low of an input impedance, and that can actually load the signal down. In some cases it doesn't matter, but in some cases it does. Now, for the alignment, it just kind of goes through, but the very last sentence is where you'll get bit. For AM alignment, short AVC to ground. Now, what is AVC? AVC is the automatic volume control. And what that is a little feedback circuit. Let's see if I can find it here. On the receiver, on the tuner. And basically when you get to the output of your last IF stage, it takes a little portion of that signal and it feeds it back into here, so that if you overdrive the input, this feedback, it works just kind of like your negative feedback loop here, it attenuates the signal. And there's a capacitor that they put in there, and that cap's job is to charge up, and it limits how fast that can react. In other words, if this weren't in there, the volume would pulsate, because every time there's a loud passage would come through the signal, it would squelch it down. So you want there to be a little delay, and that's what this does. You can increase that value a little bit, and that would increase the delay. You could decrease that value, that would decrease the delay. But this is the ideal value that belongs in the circuit. Okay, 0.047 microfarads, or 47 nanofarad. So what we want to do is we want to get rid of the influence of that. So what we're going to do is we're just going to jumper this point of the circuit directly to ground. And that's going to eliminate the influence of that AVC circuit. The problem is when you're driving your signal in there from your signal generator, if you drive too much of a signal in, the AVC is going to attenuate it. And as you're doing your alignments, you're fighting that AVC circuits. In other words, you're increasing the amplitude of the signal by peaking that coil, and the AVC is driving it down to make you think you're not doing anything. So you don't want to be throwing a dart at a moving target, right? So we want to eliminate that. Now in this particular amp, it's pretty easy to find. Let's see here, it's this 0.047 microfarad capacitor here. That's the one you want to jumper out. That's your AVC capacitor. So we're just going to take our little jumper and we're going to put it right across that capacitor like that. And we're going to just take it out of the circuit. Now what I'm going to do is I'm going to disconnect it for a moment. I'm going to go ahead and put this thing in here. So we want to attach, according to the instructions for the first test, we're going to do our intermediate frequency. You're going to take a 455 kilocycle or 455 kilohertz signal. You're going to modulate it at 30%. Again, there is no percent adjustment on your modulation knob. You're just going to turn it up a little bit, about a third of the way, at 400 hertz. So that's an audio tone. And we're going to attach this capacitor that I showed you to pin 7 of V6, which is this tube right up here. So here's pin 7 of V6 around the camera. Here, let me set some things down. And it goes in right like that. Very simple. We're then going to take our signal generator and untangle all my wires here. And I'm going to connect the negative side of my signal generator to the chassis, and the positive side, or the signal output of my generator, to that capacitor. And there, now we've just set the injection point for this signal. Now, as far as this is concerned, you're going to set your dial to 455 kilohertz. Again, with an analog meter, you're going to get it close, especially if you have to make sure with an analog signal generator, with an analog dial like this, that it's properly aligned. That alignment will change with a tube unit like this as the tubes and the capacitors and everything warm up inside there. So you have to turn this on, leave it on for 15-20 minutes and let it stabilize. and that'll give you the best frequency output. If you just buy one of these off of eBay and you haven't tested it for dial accuracy and things, you never know what your signal, what your frequency scale is going to be like. This one is dead on because I did an alignment on it and I tested it. You're going to use a fairly strong signal for the intermediate frequency because we're after the the RF amplifier stage, so you have to assume that you're creating a signal that's amplified, so you want a little bit stronger signal. So I'm on high output, and this is about halfway up. This is our RF, and then this is the amount of modulation. You can see I have it about a third of the way up, a little over that. It's not super important. I now have to attach my meter, and we're set to AC volts, and I'm on the smallest scale. Okay, and the probe is just connected right to the record out jack, where you'd connect your tape recorder from the record jacks, so we can monitor the actual signal. Now I'm going to turn this thing on, and once the receiver warms up, we have to let it warm up for about 10 minutes at least, so that everything stabilizes. And you can see I'm already getting an output. Okay, and you can see how small the output is. And if I look over here, I have the scope connected so you can kind of see what the waveform looks like. And if you take a look at that waveform does not look like a beautiful sine wave, does it? Well, welcome to the world of old tube test equipment. You're going to see this. Now, this is not a problem. As a matter of fact, with the RF portion of these old signal generators, they are purposely made to be distorted like that. That distortion causes harmonics, and those harmonics are how you're able to reach the upper frequency bands of your signal generator. I'm not going to get into that on this, but I get so many people asking about their distorted waveforms on their old tube signal generators. It's normal. That's what it's supposed to look like. All right, I hope I have everything in shot here. What I'm going to do now is, you can see where our signal strength is. And I'm not touching anything. I'm not touching the signal generator. I'm not touching the tuner, anything. But all I'm going to do is I'm going to put this jumper across that capacitor now. Okay? And watch what happens to our output. And remember, this is the audio output, what the amplifier is going to see. Okay, so here we go. Jumps for a second, and then once it stabilizes, look at that. And this is because before I jumpered this AVC circuit out of the circuit, the AVC was actually attenuating that signal that much. That's how much it attenuates the signal. That's why it's very important when you're doing an alignment of an AM tuner to take the AVC circuit out. Get rid of the influence of that so that you can align it. Everything's set up now, and we're ready to do the alignment. Now, according to this, what they want us to do is go to Z3 and Z5, top and bottom. So there's 4 adjustments. Whenever you look at these alignment cans, and you can see here's the bottom of these IF transformers, and this is where you would take your alignment tool, whatever it is. I'm just going to show this as an example. This is the wrong tool, but you would put the bottom is what they're talking about here. The top is the hole on the top of that aluminum can. Okay, so there's 4 adjustments. There's 2 transformers, and the top and bottom of each transformer, 4 adjustment points. And all you're going to do is you're going to put the alignment tool in there, and make sure you use a plastic or non-conductive one, a non-magnetic one as well. And you want to adjust those till this signal on your meter is at its maximum. All right. I'll do one to show you, but these are pretty much on. I don't think we're going to have to mess with them. So here's Z3. I marked it to be a little easier to see there. And if you just put your adjuster in there and you turn this, it's going down, so that's not the right way. And it's going down again. So you can see it was peaked. That's why I said I had a feeling this was okay. So anyway, that's it. And then you would go to the top part and do the same thing to verify that it's peaked. And I don't know if I can reach it from here. Okay, here we go. Hope I'm getting this. And you see, you adjust. That's pretty good. And it moves around. There we go. Yeah, it's peaked. So it was good. And all of them are going to be like that. So that's the process in a nutshell for what you're going to do. And you're going to go through and we're going to peak Z5. And you can see with this one, they actually want a sweep signal. So what I said at the beginning of this video here, of this segment, is that we're not going to do a sweep alignment. But here, they actually want a sweep alignment on this. Okay, so since I don't feel like digging out more test equipment and putting it on the bench, we're just going to use what we have connected already. So everything's connected to the same points as the last procedure we did. And to do this sweep alignment, fortunately, this WR50B does have a sweep mode in it. Now, it's not exactly the same as using a dedicated sweep generator, but it works. It'll work for what we're going to do. So I have it set to sweep mode up here for the modulation. And I have selected the 455 kilohertz sweep. And I believe in this mode, it actually does have a crystal oscillator. It works pretty well. I mean, this thing was aligned about a year ago, and it's working pretty well. If you notice, no, you can't notice because I'm out of frame, there's another wire connected right now. I have another cable coming from the modulation output. And this isn't the most perfect setup you can have, but it works. So going over to the scope, let's look at a few of the things. This is your S-curve, or at least this is your curve that you're looking at. This isn't the same as looking at the FM discriminator. This is a different setup, but essentially what we have is we're driving the trigger of the scope off the external input, and if you notice the other end, well, you don't notice because I don't have it in frame, the other end of that modulation out is going into the trigger input. So I'm just triggering off of that. If not, this thing would bounce back and forth at 60 hertz because that's the frequency at which it's sweeping back and forth between its, past the 455 center point. And I readjusted some of the variables in here because we don't care about, the actual amplitude, voltage, and so forth. We just want it to fill the screen and be centered. So we adjusted a few of the variable adjustments. And you can see we have our nice little slope on there. And you can see the little pip there in the middle. And the idea is when we adjusted the top and bottom slugs on Z5 in the previous alignment procedure, it should have gotten this pretty close, but it won't be perfect. And what will happen is this little zigzaggy part here, the little pip, will actually be, and I call it a pip, but really I don't have an actual marker signal on this, so I don't want to confuse you using the wrong language. But right here, you want this to be about centered on the slope. And it should be pretty close to that right out of the box when you peak everything. But you'll see that it's not going to be perfect. You'll have to fine tune it. And that's really what they have you do here. So could you skip this if you do not have a sweep generator? Yes, you could. And it's still, your alignment would be close. It just wouldn't be perfect. And if you read, it even says adjust slightly for symmetrical curve. So really they're saying that it's going to be really close and you're just going to fine tune it. And if I go into the bottom slug of Z5, you'll see what this adjustment's doing. See how that moves it? Now it's moving it up towards the top. And now as I go more, the amplitude will go through its peak. See, there's the peak. You see it on there? It's actually off the scale now. But take note that this is not centered anymore. So the idea is adjust it slightly, just like they say, till you're centered. And that's about where you want it, you know, kind of like right in the middle. And you can eyeball it. I mean, it's, you know, get it close. Right about there is where you want it to be. That should be pretty good there. If I move this, get us a little bit closer, and you can see it's right cut in the center where it should be. So that's the alignment there for that. And again, you don't have to do this if you don't. Not everybody has a sweep generator, and if you have a TV sweep generator, it's not going to help you because the TV FM sweep generators typically won't operate in the frequency you need for the AM band. So you would have to have a separate sweep generator, just an individual sweep generator, and modulate it into the modulation input of your signal generator. So a lot of work for a tiny little tweak like that, but that's all it is. Okay, for the next thing, we're going to just do the upper and lower dial accuracy, and we're going to start with 600 kilohertz. And we're going to just tune in to 600 kilohertz on the dial there. Set the signal generator to 600 kilohertz with modulation. And then we're going to adjust, you can see where it says right there, adjust L9, Z1, and L1. And we're not going to really do a lot of that. I'll just go over it with you because it's fine. And they want you to connect it to the antenna input with a 200 picofarad capacitor. And they want you to disconnect the link between the terminals. So I've done that. And you can see over here where we've removed the little jumper between the ground and this input pin. And that kind of takes the rod antenna partially out of the circuit. And then what we're going to adjust is we're going to adjust up here, which is your Z1. You're going to adjust this what is that, L9, I think it was, yeah, L9. And then L1 is up inside the tuning gang inside there. I'm not going to go in there and mess around with that. It doesn't need it. But anyway, what I want to bring to your attention is something that could throw you off. So take a look at the meter right now, what it's doing. See how it's moving around? Now, I'm not turning anything. I'm not adjusting anything, so there must be something wrong with the tuner, huh? Well, actually not. If we look over to here, can you see what the waveform is doing? It's getting cleaner, and then it's getting some kind of distortion on it. Now let me turn the volume up. You hear that? That is not my test equipment, nor is that the receiver. It's actually this up here. And you can see I have it turned sideways. This is the Rigel DG4162. And let me turn this around. Those of you who own these probably know this problem, but those of you who do not, this is a good example of what can go wrong with your test equipment. Take a look at that pulsating. Remember, this is not turned on. This is off. This is when it's in standby, it flashes that green power button to show you where the power button is. Like we really need that, right? But listen again. Yeah. So the little circuit that flashes that light to tell you that the power switch is there, like you're not smart enough to know that, causes that kind of RF interference. Now watch what happens when I unplug this. Here's the connector, right? Turn the volume up. Gone. So there's a good example of how things on your bench, even legitimate test equipment, can be a source of interference. This is why, and the funny thing is also when you turn this on, it gets rid of that as well. So it's just in standby that it does that. But you just have to kind of, again, you have to know your bench, you have to know your environment, and know your test equipment. So now that we got rid of that, we can actually do the alignment. So we're back over here, and it's a weak signal, so it is going to fluctuate around a little bit. But notice it's not near as bad as it was. And I'm just going to do these bottom ones. We'll do Z1 first. And you can see if I turn it a little bit, well, if I put the right tool in there before I turn it, you have to have the correct adjustment. There we go. And you can see, there we go. And we peaked it out. So that one could go a wee little bit. Not bad. Then we go to that L9. And you can see it took a little bit also. And then the other one on the top, maybe I will look at that, but I have to take the cover off to do that. But there you go. It's as simple as that. So the AM, at least that part of it is aligned. Then the next thing you do is you go down to 1400 kilocycles. And notice I'm not getting crazy because I don't have the digital equipment connected. Get it in the ballpark. So we're on 1400 right there. Take your tuner and adjust it to 1400. Okay, and you can see it's pretty close to 1400. Not bad. And like I said, part of it could be the dial, and part of it could be the dial on this and the angle that I'm looking at it. It doesn't really matter for this alignment as long as they're both on the same thing, and then you can peak them. That's really what the name of the game is here. So, and then I just look at the scope for the highest waveform that stays clean, you know, the highest amplitude of the waveform that stays clean still. You can see, there we go. And then again, you're going to do the same thing, except now you're going to adjust the 3 little capacitors that are on top of the tuning gang. And I always like to use a ceramic screwdriver, something that's non-metallic, to make those adjustments. And we can go in there and we can peak them. And that's it. It's adjusted. AM is aligned. And of course, if you know what you're doing and you're not trying to film a video, you could knock this out in about 15 minutes if you really know what you're doing. It's not a big deal. AM is the easy part. FM is a little more involved, and that's what we're going to do next. All right, to do this next step, you need an FM signal generator, or a generator that's capable of doing an FM signal. For this first alignment, you don't need any modulation at all, so you don't need FM, AM, or anything. You just need a straight carrier, and we need 10.7 megahertz, which is the IF frequency of the FM section. So I have it set to output just 10.7 straight carrier wave. I have a very strong signal, and you will need that. And all they have you do is attach the signal generator to the little shield. I don't know if I can show this or not. See it around there? Just attached to the shield of that first tube there. And you can hear, if I turn it up, I'll let you hear. You hear that little bit of hiss? And if I turn the signal generator down, here it gets louder. Okay, so you kind of want it to just start squelching out that hiss, make it quiet. Just you want it to, so if that makes sense. So now that that's set, we want to go to our VTVM here. And again, this is how I do it. You can do it however you want. But since I have a VTVM, this has the advantage of you can set this, see where it has a dB scale, and you can set it for positive and negative on the 0. I'm going to do that. So I'm going to go up to here. And what we're looking for in this is we want our maximum negative deflection. So you want, according to what this says, the adjustments that we would make would be Z2, 4, 6, and 7, top and bottom, maximum negative voltage. You see that? So I could set this to negative DC volts, or I could set it to positive voltage and set this to 0. That way, if you go the wrong way, you'll see that you're going the wrong way. Anyhow, if I take my probe now and connect it to test point, what are they saying? Test point 3. And test point 3 is the output of your discriminator. So I'll show you. Remember that capacitor we replaced in the last video? That one that was really, really bad and I told you it was important? Well, there it is. We're going to connect right up to it. And lo and behold, we have a negative voltage. Now I'll just adjust one of these, and I mean, it's already, everything's aligned on this. This tuner really didn't need aligned at all. But I'll show you. If I turn one of the adjustments, you can see it'll make it more positive because it's already peaked out. But if I go right there's the maximum negative I can get. See that? And that's what they're talking about. You're going to adjust them all doing that. So connecting a signal generator to that tube shield without actually touching the circuitry, that's called loose coupling. So by using a loose coupling technique, we're radiating the signal from the signal generator into that tube. And that's why I had to have a really strong signal, because I don't really have any physical connection to the circuitry. So that's why that works like that. Okay, the next thing we're going to do is we're going to set our discriminator. And there are multiple methods for doing this, but I'm going to follow what the instructions are saying here. And what they want you to do is you're leaving your signal generator still loosely coupled to that first tube there. And they want you to, so everything's the same there. And there goes the camera. And they want us to connect hot lead of DC VTVM to multiplex input. And they want you to ground to the junction of two resistors, 47K, connected in series from TSP3 to ground. What does that mean? Well, all they're saying is you're going to shunt that charge capacitor right there, the 8 microfarad, with two 47K resistors in series. So you can see what I have here, this mess. I have two 47Ks that are in series. And these two outer connectors here go across that capacitor. And then the meter is this yellow lead. And this black lead goes up to the multiplex jack. And looking at the schematic makes it a little more understandable. You can see there's the output of the discriminator. Here's your multiplex jack. Okay. There's your capacitor with test point 3. And that's what you're putting your two 47Ks in series across there, and then coming out of the center of those and going back to here. So that's all you're doing. Again, they want you to set your DC voltmeter to read center scale, just like that. Now you can use a VTV or a a DMM, you know, your multimeter, and you're setting it for 0 volts, and it'll read positive or negative. So all you're going to do is you're going to inject a signal. Don't put too strong of a signal in, or you'll swamp the whole circuit out. You want just enough to get it to deflect somewhat, and then you're going to adjust your discriminator for 0. And this one already is centered, but if it weren't, you would adjust that the top of that can until you were right on the middle there. Let me see if I can put a... Here, I'll tune it out a little bit for you so you can see what it does. See how now I'm the wrong way? It's starting to move, and then if I go the other way, it starts to move off center again. And the idea is to just get it centered, okay? And that's it. Okay, we're going to listen to a little bit of piano because my wife's playing around upstairs with the piano. So we'll get serenaded. Anyway, the next thing we're going to do is we're going to adjust our dial accuracy at 90 megahertz. And I have the signal generator set to 96 megahertz. That's what we're setting, is 96, I'm sorry. Oh, we want it to be 90. So let's... help if we set this right, huh? (90 megahertz). We want 400 hertz modulation, and we want 30% modulation. It's hard to see here with this. And I'm going to go down to the tuner. We're going to set it to 90 megahertz down here. Okay, and somewhere in here we should cross through it. Now, here's the thing. I'm not going to use the dial to set this. Okay, you can see it's right about at 90 now. I'm going to use my scope. And I have a weak enough signal. I'm going to pass through here. And you can see what we have. See how we have an equal amount? And I can turn the signal strength up and it'll clean up. But I'm turning the signal strength of the signal generator down till I get this little bit of interference on the top and the bottom of the waveform. And I want it to look symmetrical. So when I tune through this, see how the top now is getting more static than the bottom? And then if I go the other direction, see how the bottom gets more? What we want to do is we want to adjust it till they're both the same. See that? Now, what I will tell you is if the discriminator were not properly aligned in that last procedure, you would be able to get the static to get bigger on one side, but it wouldn't get bigger on the other side as you pass through it. It would look, no matter how you tuned it, you would never be able to get it to pass through correctly. So that's a good test that you can do. And if you listen to it, I have just enough static that you can hear it. Hear that little bit of static in the background? That's what we want. And now that that's set up, you could go through and you can do your alignment, and that's where you're going to set your L6, L5, and L2. And what they have you do, I'm sorry I forgot to show you this, you take two 120 ohm resistors, and they want carbon resistors. And the reason they say that is back in the day, they didn't want you to put a wire wound resistor because the wire wound resistors had inductance, and that would affect your signal. Now this is a spiral cut metal film resistor, but because of how tiny it is and how tiny the spiral is, the inductance will not make any difference in this test. So we can use these resistors safely. And then they have you go back to your multiplex output, and they want you to tune it for maximum negative voltage. So you can see we have a negative voltage with respect to our 0 mark again. And so you just go through and you adjust L6, L5, and L2. Then we tune up to 106 megahertz and do the same thing with C22 and C17. They're perfect, so I'm not going to touch them. And just so we can see where our dial accuracy is, remember we never looked at the dial. We used the scope and the waveform. And if we look over here, we're pretty darn close to being right on 90 megahertz. Now I'm looking at an angle with the camera, so it makes it look like it's off, but it's dead on. So this thing does not need aligned. Okay, that's it. The tuner is aligned, but the multiplex is not, and there is no procedure in the book for that. Back when this thing was made, multiplex was a fairly new technology, and almost no radio shop had the proper signal generators to generate a composite multiplex signal, so they left that part out. And the idea was you never touched the alignment in these. You left them as is, and you never touched it.